loud. Right now we're recording. So we'll cover these next, 5 sections over the next 2 weeks. I'll probably also try to have an activity planned as well to finish it out. I haven't built it yet, but I'll kind of how we finish up the chapter with a little activity. I get that added. So today is kind of a definition day. We might get into a little bit of 8.2, but I'll probably do most of 8.2 on Thursday. And then maybe kind of get into a little of 8.3, and then we can do 8.4 and 8.5 next week. And again, we're just scratching the surface. If you take 135, there is basically a week at least dedicated or more to each of these sections. So we're just covering the basics here. We're not going to get too in depth in our QR class. And then when you take statistics, you'll get a much in-depth definition. So 8.1 is very definition heavy. It's about collecting data. So it's a lot of just definitions. So all data is a collection of observations. I like to say we use the symbol X, and the reason I do that is because it's a common symbol in algebra, but it's a common symbol in all of the formulas in statistics. So data is represented by a kind of X, and data can be quantitative or qualitative. I call it categorical. So basically data can be represented by a number, or it can be represented by a name. And sometimes it can be done by both, right? So if you think about grades for anything, you can get A, B, C, D, or an F, which would be categorical data, or qualitative. And then, or I can assign numbers, 90%, 80%, 70%, and can be quantitative. So that is the kind of neat thing with data. You can kind of manipulate it sometimes to fall into more than one category. Typically, we want things to be quantitative because then we can do calculations. There is ways to do qualitative statistical analysis. It can be a little tricky at times, but once you kind of get the concepts down, it's not too bad. So statistics, basically all that is analyzing data, right? I've got the full definition of the book written into my OneNote so you can see it, but I'm going to summarize these because you all can read. But that's all statistics is just analyzing, interpreting results. And the key to it is drawing a conclusion, right? We want to be able to look at the data and make some kind of decision, right? And that's being used currently in a situation we're in with the coronavirus, right? So social isolation was kind of put into place based on statistical analysis. The president is talking about trying to open up the economy based on hopefully some statistical analysis. That's very argumentative of how he's using his statistical analysis to make informed decisions. Some argue he's not. And sometimes I feel that way just based on the speeches. But hopefully someone is getting him to kind of see the statistics behind what we're doing. So a population is the complete data set. I like to think of it more as something of infinite size or unmeasurable. Most populations are this. Now, can you have a population that you can measure? Yes. If you make a very specific item that only you have the data of, and you have all of the data, then you could actually have your true population. However, I like to think of things as infinite size because most of the time we don't have that information, right? We can estimate the number of people on the planet, but we don't know precisely exactly how many people are on the planet. We can estimate the number of people that have coronavirus, but we don't know exactly how many people have it. So that's why I always think of it a population as of infinite size, right? It's impossible to measure everyone because it's either always changing or it's just so large you just can't measure it. A census, which is uniquely what we're in right now for the United States, is when you try to collect data from every member of the population. And I like the word try. They say it is a collection, but I don't believe when we do our census that we actually talk or get the accurate of 100% of everybody. We get as close as we can, and then we make decisions based off it. A
Just remind me, I
sample.
still got to do my census.
I know I did on mine online. I was surprised they didn't come out and wait till afterwards, is with all the things going on to get it to settle down. But yeah, I did mine online. It actually was pretty quick. They did a good job at creating the little online census.
Good.
A sample is a subset from the population, and that's what most of us will in statistics do, right? We get a sample of a population, and that's what we actually do statistical analysis on. The parameter is basically a numerical measurement that describes a population, while a statistic is a numerical measurement that describes a sample. And so one of the things, and you'll see this again if you take statistics with me, is understanding the difference between these. So I'm going to try to give myself enough room to write here. Let's see, draw. Make me a little table here. So I will have, well, I can write it first. That would be a little bit neater. I will have, let's see here. Where's my cursor? There we go. So we have, I'm trying to think what my table looks like now. Over this, there we go. We have our statistic. We won't call it that. Let's call our, yeah, we'll call it statistics. Statistics, there we go. Why is my tab not working? Let's do a bunch of spaces then. And then we have our population, parameter, we have our sample statistic. I'm not sure why my computer is not cooperating with me all of a sudden. Or whatever. Undo. Why am I in draw? That's probably half my problem. So our statistics, there we go. We will have the mean. We will have the proportion. We'll have the variance. We'll have our standard deviation. We'll have our size. Now I'm going to go to draw because I don't want to try to figure out getting this thing to mimic all my symbols. So the symbol for a population parameter for the mean is a what we call a mu, kind of a backwards y. And then our sample statistic of the mean is an x bar. For a proportion, it is a p. And then for our sample statistic, it is a p with a hat on it. Variance is a sigma squared. And then our sample statistic is, ooh, I don't know why that just did that. Erase. Is a s squared. Standard deviation is a sigma. And our standard deviation sample statistic is an s. And then finally, let's see if I can come up with another color here. We'll do orange. Our sample size is a capital N, and our sample statistic is an N. So our population is a capital N, and our sample is a little n. So these are kind of the symbols. And so when we get into statistics, one thing I try to really get my students to realize, these, remember, go play. Sorry, my dog barking at me, wants me to play with her.
I already know.
She wants, sorry, now I lost my train of thought to my dog. The samples that these statistics are probably the most common, right? And I tell my students that the quicker you gain an understanding of these, the easier statistics will be. So in my stats class right now, this is kind of the breaking point. The students that kind of understand these symbols are kind of doing pretty decent with the statistical analysis. Ones that still have no idea what these symbols are the ones that are typically completely lost right now. And it's really important to know the difference between these in statistical analysis, right? Because you can see we have a mean, but it has two different symbols. So depending which world you're standing in, if I am in the population, then I have the mean mu. If I am basing it off my sample statistic, I have X bar. And we'll get into how to calculate these in this class a little bit, and then we'll do way more when we get into statistics. So don't worry about how to find these values yet. Today's lesson, I'm more concerned that you understand what they represent. So the mean is what we expect to happen. And most of you probably know how to find the sample mean, because how do you find the average of something? Well, you add up all the data and you divide by how many you have, right? But that is a sample, so that actually is X bar. Now, if you could technically get all your values from the population, then you could still do the same thing, add up everything and divide by how many you have. However, because you can't typically find everything in the population, there's other ways to find the population mean, and we'll get into those later on. Proportion is just a fancy way of saying probability. So this goes back to chapter 7. How do we find the proportion of something? Well, success over total. Now, the difference is if the proportion is based on the population, then it's represented by P. If the proportion is based on a statistic, then it's represented by P hat. And most of the time, a lot of times we will say something is of the population P when it's really not. For example, the proportion of people who have coronavirus that the news keeps reporting every day, I will argue, is a sample, because we don't know the true number of people who have coronavirus. All we know is the number that states are reporting, which is based on maybe some test kits or some data they have. So therefore, it is actually a sample. So therefore, it is actually P hat. And so that's kind of what these symbols all kind of walk us through, is knowing the difference of the two. And why this is so important, in statistics, really all we're trying to do is ask ourselves, how close are these related? Right? And that's really what statistics does. Is X bar a good representation of the population mean? Is P hat, the sample proportion, a good representation of the true proportion? Is standard deviation a good representation of the population standard deviation? And really, this one shouldn't have an equals, because N is just how many samples you took, and big N is how many you are. So they're never going to equal unless you actually take everybody. So those we don't actually compare, but they're important symbols because we use them a lot. Kind of, that's why I have them in my table. So this is a good rundown of everything that we will basically cover in our chapter, and what we'll spend 16 weeks doing in actual statistics class. Any questions so far? Get off my draw here. All right. Now, another thing that we really have to consider is things are discrete or continuous. And again, in here, we're talking events. And I'm not even going to go into all the definitions of the book. How I look at something that is discrete, it's kind of a whole number, versus something that's continuous is a real number. And the easiest way for me to tell the difference between something that's discrete or continuous is if I take my event, which we learned in chapter 7, and if I can divide it by 2 and it still makes sense, that's continuous. So a couple examples here. If I'm counting people, right, the number of people with coronavirus, I can't have half a person. Therefore, that is a discrete thing. And that's why it's a whole number. I have 1 person, 2 person, 3 person, 4 person, 5 person. So therefore, that event is discrete. If I am looking how many days someone is sick with the coronavirus, right? Even though I can count 1 day, 2 day, 3 day, 4 day, 5 day, I can also count a half a day. or a quarter of a day. And since I can break days down to smaller pieces, that is continuous, right? And that's why I'm always cautious of how authors put things in for definitions in their books, because I feel like sometimes they oversimplify it. Because a lot of times, like in the stats book, it calls something as continuous is something that's unmeasurable or uncountable. Well, I can count how many days someone is sick, so I don't like that definition. I prefer the one where continuous means I can keep breaking down smaller and it still makes sense. And that's why the author says things are uncountable, because I can keep breaking it down smaller, which makes it difficult to actually count. And we're actually counting by rounding. So big takeaway, and this is important, not so much in going to be in this class, a little bit, but in statistics, it really is, because the calculations change depending on if you're discrete or continuous. So you must know, is your event discrete or continuous? And then you must know, are you looking at the population or are you looking at a sample? And that's what makes statistics hard, really, is knowing what world you're in, not so much the math. The math in statistics is really not too bad, because it's a lot of adding, subtracting. But the challenging part is knowing the difference of where you lie. So no, ignore that page number, because that's wrong book. So I'll leave that out of there anyway. So an observational study versus an experiment, right? So in an observational study, we observe things. And we've talked about this before, I think, in this class. You collect and measure specific characteristics, but you don't attempt to modify the things that are being studied, right? So counting how many people have coronavirus, even though we are kind of modifying it because we're telling who can take the test or not. So this one could be very arguable which way we would call it. But if we weren't doing that piece, we're just observing. An experiment, though, is when you put something in control. And this is kind of done a lot in the medical field, right? So one of the theories to try to combat the coronavirus is to take someone who has had it and recovered and take some of their blood and give it to someone that is not recovering so well, to try to give them some antibodies, right? And that would be an experiment, because now you're controlling who gets the antibodies or not, to see if there is a true result in antibodies. Typically, I don't put a lot of emphasis on this, even in my stats class, because this is something more that a statistician really cares about. Most people in the real world get these two things mixed up a lot when they're talking, and I still do sometimes, what I call an observational study or an experiment. But the easiest way to know the difference between the two is an experiment is you're putting something under control. You're controlling how the subjects are being tested. Versus an observational study, you're literally just collecting the data and letting the data speak for itself, and you're not picking or choosing, manipulating it in any way. Any questions on, and please interrupt me or send me a chat or something if I'm going too fast on the definition pieces here. So types of sampling. So to make something in statistics, we want to try to make it unbiased. We don't want our data to be misleading. So we want to try to make it unbiased. And the best way to do that is these different types of sampling. So a random sample is each subject of the population has the same chance of being selected. So if someone in the population has a higher chance of being selected versus another, then your data is not unbiased, right? So we want to make things have equal chance of being selected. Versus if everybody has the same chance of being selected, then it is considered random. And that's actually really challenging to do, because no matter what you do, you increase the likelihood of someone else being selected just because of the way you collect your sample. And that's why typically you want to try to do some of these other types of things so you don't. So say you are trying to do a phone survey to collect some data. Well, the problem is you're already changing the likelihood of people being selected depending on, you have to have a phone to be selected. So if you don't have a phone, then you don't have a chance of even being contacted, right? So therefore, not everybody in the population has the same chance. So it is not random. That's why a lot of times people do mails, orders, in person, and phones for like the census to try to get to everybody. But it is very, very challenging. A representative of a population means it must have the same characteristics of that population. I mean, it doesn't favor one group of the population over another, right? So you want a good representation of your population. And this is also challenging, right? So we live in Maine, and say we want to look at, compare our coronavirus numbers to other states. Well, we can't just say the numbers in Maine represent the entire country, because we don't have the same characteristics of, say, like New York or other in California, where it has way more bigger cities, more people. We're more rural. So that's what it talks about, relevant characteristics. The two populations have to be similar. And that's what it kind of, if you watch the news, depending on what side you're standing on in this situation, there's a lot of argument where we should have the same rules for all 50 states, but all 50 states don't represent each other the same. So this is where it gets very challenging. So it's the types of sampling that try to get things to be random and give everybody an equal chance of these. So systematic means you start at some point, then you select every case, right? So you are going to
word. KTH, that's a word.
Yeah, it's supposed to have a little subscript on. I gotta figure out how to get let's see if I can do it here. Case. Yeah, so I gotta figure out how to get that thing to go up. It's this. I'm not sure. Oh, there we go. Superscript. There we go. Case. So what you do is, say you're gonna talk to every 10th person, right? So you talk to the first person, and then after they leave, you count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the next person, as the 10th person in line, you now interview them. And as long as you stick to that same pattern, that is systematic, right? So systematic basically, and you have to do this before you start collecting data. You can't change, like, all right, every 10th person is taking way too long, so I'm going to change it to the every 5th now. All right, so once you pick what you're going to talk to, you stick with it. So, you know, if I'm on CMCC campus and I want to get an opinion of how things are going with everybody doing this social distancing, and I talk to every 10th person that comes to the door, then I ignore the 9 in between. That's systematic. Convenience is typically what most data is. Convenience means the results are easy to collect. Grabbing numbers from numbers that are reported to the CDC, all that is kind of convenience. They didn't do any type of sampling. They're just basically collecting data any way they can, and that's considered a convenience sample. Stratified is when I take my population and I divide it into 2 or more groups of some characteristic. Then I sample a little bit from each group. So say I want to break my groups into male or female, right? And then once I put everybody into male and female, then I pick a couple from a certain number from each group. That's stratified. Cluster is I divide the population into groups, and then I randomly select some of the clusters to talk to, but I talk to everybody in that cluster. So say I break the population down by age groups. People in their 20s, 30s, 40s, 50s, 60s, 70s, 80s, 90s. Right, so now I've taken the population and broken them down into these clusters. And then I am going to pick everyone in their 30s and everyone in their 50s and everyone in their 70s. And as long as I talk to everyone in that subgroup, then that is what clustering. So the big difference is both of them get broken into groups. Stratified, I pick a few from each group and I talk to them. Cluster is I pick a few groups and I talk to everybody in that group. Kind of clear? All right.
Sounds
Voluntary response is the worst type of sampling, but it's one we use a lot, right? Involuntary response is when subjects decide if they will participate or not. The issue with this is your data is typically extremely biased, right? So think about it when you go to restaurants or stores, they always say, hey, if you complete this little survey at the bottom of this receipt, we will give you a free cheeseburger, right? So typically, think about it, how many of you actually have participated in any of those surveys? Typically, if you participate in the survey, usually you're upset about something.
I've never.
Yeah, me neither. No matter how much they bribe me, I don't. But people that usually do are ones that are extremely upset about something, or maybe you're lucky enough and you're extremely happy about something. So that doesn't represent the public really well, right? So you get these surveys and people fill them out. Typically, only if you do a bad, so all you get is negative survey results, which might not actually represent the population accurately. The problem is most of the people that feel indifferent to something just don't respond. So that's why voluntary responses are so horrible. And really, this is what's the problem with, what's it called? I forgot the name of it. Exit polling, right? When we try to make predictions off exit polling, and this happened really big with President Trump versus Hillary Clinton in their previous election. People voted. Most of the people that would do the exit polls were voluntary responses, and they mostly said they voted for Hillary. And people that voted for Trump didn't respond typically, except for unless they were diehard Trump fans, right? So the exit polls showed Hillary destroying him almost in every state. But the problem is it was a voluntary response. You know, when you got a bunch of people outside cheering for Hillary and you vote for Trump, you're probably not going to walk up to the person and say, yeah, I'm a Trump, because then you're just going to get harassed and heckled, especially depending on where you live. So
Exactly.
most of the Trump people that voted came out of the polling, and when they asked, hey, do you want to comment who you voted for? The answer is no comment. So the only people they included in the survey were the ones that were responding to Hillary, which showed in that election why the exit polls showed her winning way more than she actually was winning. That's the problem with voluntary responses. You only get responses from the people that want to respond. So it does not represent your data very well. That's a quick rundown of some of the key definitions. The really big takeaways that I really want you to be able to go with is our little cool table here of the different symbols and what they represent. Discrete versus continuous, because that really comes down to some of the different formulas for calculation, and kind of realizing a parameter represents a population and a statistic represents a sample, which goes back to our population and sample up here. So that's kind of how these things all relate in kind of 8.1. So 8.1 goes through and kind of breaks all of these definitions down. Not a lot of calculations, but just what things mean. And not all of it's in the book. I added a few things like this little table, something I came up with, because this is where I'll spend most of our time in intro statistics calculating these things. Any questions before we move on to 8.2?
Don't think so.
All right. Well, it's just a quick overview of definitions. So 8.2 is how to display data, right? And so a lot of this is very kind of what I go into in 135, and we spent a lot of time on histograms in 135. So what I'm going to do in this course is I still put the information in so you can see it, but we're going to kind of talk about some of the types of graphs and what they are, and then we will go into kind of building these things probably next class. So I'll have an Excel file and stuff where we can kind of do a visual of displaying data next class. But we'll just kind of talk about these graphs are today and probably call it a day, because I got to get the Excel file, what one I want that's going to represent this stuff really good. So let's just talk about some types of charts. And some of these you've seen, and there's more charts than just listed here, obviously. These are kind of the big ones that we kind of like to talk about. So a pie chart, right? And pie charts are interesting depending on who you talk to. So if you talk to a statistician or someone who does analysis with data, there is a huge argument in our field that pie charts should just be banned and thrown away and they're the devil. Because there's a huge argument, and I don't know how true it is, but supposedly the human brain cannot process angles accurately, so therefore a pie chart cannot be measured right. I don't understand that because I can look at an angle and tell if it's, bigger than 90 or not. But that's their argument of why we shouldn't use pie charts. But basically, all a pie chart is, if I can draw one here, and I know we've all seen them before. I don't think we have any psych majors. If we did, they can explain to me the whole concept of why this pie charts are bad. But pie chart is just a circle, right? Like a pizza. And you kind of break it into pieces. And each piece represents something, right?
I'm a psych major,
So-
Chris.
You what?
I'm
Yeah,
a psych
so maybe-
major, but I don't
There you
know
go.
crap about that.
Yeah,
Not yet,
so some
anyway.
argument about the brain not being able to distinguish the angle or something. But
Interesting. I'll have to look into that. I'll let you know my thoughts.
okay,
Yeah, I don't know. I saw one thing in psychology about, it's about what you have for references. And so there's an optical illusion where if you look at, say the corner of the room makes kind of like a Y. And so if you draw that on 2D, somebody in the Western world or somebody grows up in houses can recognize that as the corner of a room. But you go and you show that to a Mongolian who lives in a yurt, and they don't recognize it as being three-dimensional. It just looks like a Y to them. The optical illusion doesn't work on them. So, like if people saw pie graphs and worked with them, then they could see the statistics in them.
Gotcha. So it's
Yeah.
more like a point of reference perspective type thing.
Yeah, I feel like pie charts don't work because we don't use them.
yeah, I like that answer because I guess
That's a
I've
good
seen them,
one.
so they make sense to me. But so because there's a pie chart, and pie charts are typically, not always, they can be quantitative, but for some reason, a lot of people say they're categorical. So I made this one categorical. But so say we had a three response survey where you yes, no, maybe, and then I can create my pie chart to represent a portion of the yeses, a portion of the no's, and a portion of the maybes, right? So that's kind of how a pie chart is broken down, and it's how you can display data. A bar graph, which I say is very similar to a histogram, which you haven't got into, but it is just the same thing as this pie chart. So I can have it as categorical, and again, I can have a bar for my yeses, and I can have a bar for my no's, then I can have a bar for my maybes. Right, so this is our yes, this is our no, and here's our maybe. So you're taking your results and you're just creating a chart of categorical data. A side-by-side bar graph basically is I could have the same thing, yes, no, maybe, but what I can break it down to, give me some room here, so let me get out of draw. Escape. Put some enters in here to give me some room to color. I can still do a side-by-side graph of the same categorical data. Right. Home. Escape. There we go. And I can do men. Oh, now my tabs are going to work. And women. And I can still do the same kind of situation where I have my green being my yeses, my red being my no's, my black being my maybes. And then I can also have the same data now for women. So I can have green being my yeses, red being my no's, and black being my maybes. So that's what side by side is, because now I have these two graphs, and now I'm comparing. And so this is how I could do my, not cluster, what's the other one? Stratified, right? I can break them into groups, and I can talk to so many, and then I can answer the questions, and now I can put a bar graph that represents these things. And same with my pie chart. No, yes, maybe. Yes, no, maybe. So this one would represent everyone together, right? So there's my total of my survey results. And then I can create a side-by-side to break it into my groups. And that's really the only difference of these kind of things. I gotta I move my things around, but my boxes aren't going where I want them to go. Escape. Come here, you. Let's get you out of the way. Let's grab you now. Now you're out of the way. So a stack bar graph is basically almost a side-by-side, but instead of being side-by-side, they're stacked. So now I can, again, do men and women, but instead of putting it side-by-side, I can say, here are my yeses, and then on top of that will be my no's, and then on top of that will be my maybes. So what this graph shows me is my total results of how many men answered the question versus how many women answered the question, kind of really all stacked together. So depending what you're trying to show really comes down to what you're trying to show. Sorry, don't repeat myself there. You know, so the stack bar graph shows that, hey, I had way more women participate in the survey than the men, versus my side-by-side graph, instead of comparing how many of each was more important, I want to compare the results more together. So it really comes down to how you want to display your data, which one best represents each other. Does that kind of make sense, the difference between these two? And it really comes down to you doing the analysis, which out of these four graphs, because they all kind of represent the same thing, right? My pie chart, no, yes, maybe, is the same as my bar graph of yes, no, maybe. One's just a pie chart, one is a bar graph. My side-by-side lets me break it into groups and then share each other's results with them, versus my stack bar graph, which still takes my groups, but it stacks their responses on top of each other, which is a good way to show more of the total than it is showing them broken down into groups. And these are all really good for categorical data. Now, can you do numerical data? Yes. Typically, when we do numerical data, we call it a histogram, which we'll get into in a minute. Yeah, we might get into it a little bit to at least talk the concept, and then we'll build them next class. Well, these type of graphs are very categorical data. A line graph, or typically sometimes called a scatter plot or a time series. These are good to use to compare two or more data points. And of course, if one of the data points is time, that's where we call it a time series graph. Or a scatter plot is when they're basically not time. And you can create multiple line graphs if you're comparing different populations of the same data. So a scatter plot is exactly what you kind of do in algebra class, right? So you have a y, you have an x, and you just start plotting some points. And that's all a scatter plot is. Versus a time series is the same thing. You have a y and you have an x, but in this case, x is time. And then again, you plot some points. Now, what these graphs are really good at showing us is if there's some kind of relationship, right? So at this one, you know, as x increases and y increases, the plots are really over the place, so it doesn't look like there's any kind of relationship there. Versus this one, as X increases, Y seems to be going up. So there is kind of a relationship. And which this takes us back to chapter 5 of our math modeling, right? Math modeling, we built scatter plots and we tried to fit a math model to make predictions. There is a similarity here. And I think Dylan brought it up, kind of in that modeling class, this thing called regression, right? So linear regression is a type of statistical analysis that uses math modeling based off scatter plots. So we will kind of finish that in this at the end of our statistics course, but it is based on scatter plot. And just like our course, I think this is a very interesting course, is a lot of things seem to repeat themselves, right? So now we're here in statistics and we're doing this thing, which is very similar to when we're in chapter 5 doing math modeling. All right, and then chapters 2 and 3, where we had different ways of doing subsets and set notation and truth tables, they all kind of told us the different things and they were just written differently. So there's lots of ways to display things. You just got to kind of understand what works best for you. And so those are those type of graphs. And if we come up here, we get into histograms. And histogram is a lot like a bar chart. It's that, though, what we're end up going to having is everything is kind of predetermined, where frequency becomes our label here, and down here becomes what we call our classes. Right, and so the example I used earlier is if we break this thing down by, say, our classes are our age groups that I talked about before, right? So we could have our age group, our 20s, and we could have an age group of our 30s, and an age group of our 40s, and then we'll pick another color, we'll do orange again, maybe our 50s, right? And then depending on what we're asking or what we're counting, our frequency breaks it down to how high they go, right? So that's so it looks very similar, and I think it's not really nitpicking, it is a true thing, but typically when you have a histogram, it is all numerical data versus a bar graph, which is categorical, but they show the same thing, right? They show how many respondents or how often something happens done by some kind of grouping. So our definition of frequency is how our data is partitioned based on the categories or classes, and then quantified by the number of data points in the assigned class. A relative frequency is I basically take my frequencies and I turn them into percentages. Well, how do we make something a percentage? Success over total. So we just take our number frequency and divide by the total number of people that participated, and it turns everything into a percentage. So that is really the only difference between these things. Is do you want your frequency to be a number or do you want it to be a percentage? So now there's some key definitions that we have to kind of go over before we go into how do we build these things.
So if I'm looking at a bar graph of like age groups and voting, that's a histogram?
Yes.
Okay. All right.
Yep. Yep, because in each age group, all right, and I can try to put some numbers above them. So if this is, say we had 10 people that were in the age group 20 that participated, and this one is a little bit higher, so we'll say that's 15. That's ugly 15, so we'll call it 16, so it's more like 6 now. And this bar, the blue and the red are about the same, so maybe that's also a 10. And then our orange is a little bit lower, so that's about an 8, right? So the frequency of these ages, so whatever I was doing a survey of, my 20, I had 10 20s, people in their 20s who answered the survey, 16 people in their 30s, 10 in their 40s, and 8 in their 50s that participated in whatever I'm asking. So this would be my frequency. So this would be the number 10 right here. And then a little bit lower would be an 8. And then up here would be our 16, right? And then here we'd put our ages. So 20, 30s, 40s, and 50s. Versus down here, you know, where we had men and women, and then yes, no, maybe. It's categorical, and I could still have numbers, and that's what makes it very challenging between these kind of things, right? And that's why I never really I'm too worried about someone going between a histogram and a bar graph. The issue is why histograms have to be numerical data, because these things have now formulas. So the class limits is the lower and upper. So 20 to 29 would be my class limit, right? And then this class limit would be 30 to 39, because basically once I cross over the class limit, I've gone into a new category, right? And what's tricky about this is class width. Class width is something that doesn't compute right away with a lot of people because they just try to do arithmetic, right? So the class width is the size of each class. So if we look at our here, my class width is actually 10. And people will, 20 to 29 is not 10, but if you use your fingers, it is, right? Because 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, if I count with my fingers, all 10 fingers are up. A lot of times people try to do arithmetic and they do 29 minus 20, which gives me 9, and they think their class width is 9. But because that first number is included, you actually are 1 higher than you really are. So our class width for our histogram we have drawn here is actually 10. Our class limits are the ages, 20 through 29, 30 through 39, 40 through 49, 50 through 59, right? Our boundaries are something is a way to make sure we don't accidentally miss something. And I guess ages are good because some people like to count things in half. So if someone's 29 and a half, do you put them into their 20s or do you put them into their 30s, right? Do you round up? Do you round down? And there is a way just to use logic, but there's also a way to use math. And there's actually a math formula for class boundaries, which says I take my limits and I put them together. And we'll do all the calculations next, guys. So I'm just going to kind of go through the definitions today. The midpoint is the middle of each bar, right? And you can calculate it by formula, saying the lower class limit plus your upper class limit divided by 2 is the math formula. But if you think about it, 20 to 29, what is the middle? Well, it's 25, 21, 20, 20, 21, 22, 23, 20, well, actually it's 24 and a half, I think, if you do out the math. But it is the middle number of the years. So these are kind of the definitions to create what we call a frequency table. And then you use your frequency table to create a histogram. Well, as we said before, relative frequency histogram is just you turn everything into percentages, a histogram. And so why do we build histograms? Well, in statistics, we want to look at the shape of our data. And typically, we want our data to be bell-shaped. We want our data to look like a lovely bell curve, which I'm pretty sure by now Brian is tired of hearing this bell curve thing.
That may be an understatement.
Yes. And the reason for that is in intro statistics, all the formulas that we do, your data has to be from a normal distribution, which is this bell curve. And we'll get into a little bit of what a normal distribution is at 8.4. But we build a histogram so we can see what our data looks like. So important uses of a histogram. It tells us the shape of our data. It shows us where the center is, which we call our median, which we'll spend next class how to actually calculate. It shows us the spread of our data, right? So do we have a wide bell curve like I have here, or do you get a nice tight narrow bell curve like that, right? So it can show us our distribution of our data. And both of these are symmetric, but our data doesn't have to be. It could look something like this, where we have a long tail, which means I have outliers. There's something way out here that's pulling my graph out there, and we typically call that an outlier. And so we can tell if things are skewed or symmetric. Symmetric being bell-shaped, skewed being like this. Now, I like to think of these to make my life easier. So something that's right skewed has a longer right tail. So this would be right skewed, the graph I drew. I like to say, look at it like it's your big foot. So here's your little, your big toe, and then it slowly starts to go down, and it comes way out here to your little pinky toe, right? So it looks like a right foot. So this is right skewed, versus another one that kind of goes like this, be left skewed. I don't know why I got my tux box there. And again, because it kind of looks like your left foot. Your pinky toe's here, and then it comes out to your big toe. But that's the math terms of it. And so building a histogram really tells us these things, and that's why it's extremely important. The problem with histograms, though, we'll see this when we build them, is they can be very biased. And what makes them biased is your class width. You, as the statistician, need to decide your class width, right? So I can make any class width. I can find a class width that will make my data bell-shaped every single time. So that's where we have to be really careful. And there is formulas out there that help you pick the right class width, but sometimes it just makes sense, right? I don't need to do a formula because we know age groups. We know someone who's in their 20s, right? If you're in your 20s, ages 20 to 29, then that is it. So I don't have to do a math formula to see that class width. If I'm looking at the seasons of a year, we know there's 4 seasons in a year, and there's 12 months in a year. So 12 divided by 4 is 3. So each season is 3 months long. So sometimes your class widths are easy to come up with. Other times they're more difficult, right? If I am trying to build a histogram of how many people have coronavirus, now I have to come up with this class width that actually represents things really well. And that can be a little more challenging, and that's when you can easily skew your data. So I think for next class, what we'll do is I'll get an Excel file loaded, and we'll build some of these charts so we can kind of see them with numbers and what they look like in Excel. So that will help us display the data. And then we'll get into what analyzing data is, and then we'll use that same Excel sheet, some of the calculations on how we analyze data. And that kind of is a quick down and dirty of the first part of statistics. And I said, we're just scratching the surface in this class. When we get into statistics, I mean, that right there, 8.1 through 8.5 is almost the entire semester. So chapter 7 and 8 is the full semester of statistics that we covered in 4 weeks. We'll go deeper and cover it in 16. Any questions? And we've covered today. Lots of definitions. And like I said, we'll play with some calculations next time, and we'll continue on into E2 and E3 next class. So we still got about 15 minutes left of class. If anyone does have any questions or has questions on projects or anything else they want to talk, I am here.
Where did you say the video